Well, good evening, everyone. Tonight's webinar for the Deep Reinforcement Learning Nano Degree program is going to be on PyTorch. It's an important lesson of sorts because you'll be using PyTorch throughout all the projects in this course. So it's really important to understand how PyTorch is used. And tonight I'll give you a quick introduction to some of the key ways that is done. I'll be using, as an example, the Lunar Lander project. And that's like a preliminary project that you'll do before the first real navigation project that counts for part of your grade in passing this course. But you'll use that baseline to implement the navigation. So I thought we'd take a look at that as a good example of PyTorch and how it's used. So with that, let's pull up the slides for today, and we'll get started. Okay. So as I mentioned, the objective today is to talk about PyTorch and how that framework is used in deep reinforcement learning. I'll use DQN as an example of an implementation architecture, and you'll be seeing several different agents throughout this course, but the first one that you really get into pretty deep is DQN, so we'll use that as our first example. And then once you define the model, the agent itself will use that model to do its activities and obtain actions through the model to obtain Q values, and we'll show how that all works in the process of going through this. All right, so Q network is an example model, and again, this is from the Lunar Lander project, and this code segment here is entirely the model.py file from that project. And this model.py, pretty standard through all of deep reinforcement learning. You'll have two kind of major helper files that you'll use. One is a model.py and one is an agent.py. And the model.py defines the neural network models that you use. And agent.py then has all the actions in it for taking an action, taking a step, learning, all those different activities. So here, the first thing, defining a model. And I'll go through this in 3 sections. So I wasn't quite sure how well this would be visible at the resolution to show everything on one page. So this first page that you see here is just the full introduction. And I broke it up into the 3 sections you see there. The first one, just the imports and the declaration of the class that defines this model. And then the second step will be to define the initialization code for when you instantiate this model. And then the last section is what happens when you perform a forward pass through the network. So let's touch on each of those in turn here. So to start with, I should mention that PyTorch is a quite large collection of a code baseline. There's quite a few different containers. Each one of these containers has quite a few different packages, and each of the packages have different containers. So the full set of all the packages is in a documentation link, and I've given the link there. You can go to pytorch.org into the docs folder, and you'll see all the different packages that PyTorch has available. One that you'll use in this particular application a lot is the NN package. And inside that package, there's 3 different containers that you use. Again, there's several others in here that you're not going to be using. And it's worth your while to pull up that documentation page and kind of peruse through what's available. But I'll just touch on the main sections out of this that actually get used in the Lunar Lander project as an example. So the first of these imports is the torch.nn.module container, and that container basically should be used as the base class for any models that you develop, any neural network models that you develop. And we'll see how we declare this new class you're going to build for your particular model, for your deep learning project as a subclass of torch.nn.module. I should mention too, the torch should be not capitalized there. Should just be a lowercase t. So the second sort of major container that you work a lot with, and there's quite a few things in this one also, is the nn.functional. And this basically has all the different activation functions that are available to you. All the common ones that you could think of, and if you look at the documentation, there's several that you may not have and probably have never heard of before. But the ones that you'll see a lot in deep reinforcement learning include ReLU, TANH, and softmax. Those are definitely in there, along with many others. And the last one that we'll use in this model is torch.nn.linear. And this basically is the function that you'll use to define a fully connected layer in a neural network. And in the models that we're using here, they're all fully connected. So we'll be using this extensively in this particular example. When you call torch.nn.linear, you have to pass in the size of the input features and the size of the output features, and whether you want to use a bias or not. And essentially, it just produces an output y by multiplying the input x times a weight matrix, here termed A transpose is the weight matrix, and adds a bias. You can choose to learn with the bias or without. Just set it to true or false, whether you want to use that or not. Okay, again, here's the first half a dozen lines. Basically import those three containers we just talked about, and then instantiate your new class, which we call here QNetwork, as a subclass of nn.module. Pretty straightforward. Okay, the next section is the init method, and basically you'll be initializing your class with the size of your state, the size of the output actions, a random seed, and then some hyperparameters for the sizes of the different layers. And we'll look at that here. This is basically that section in a little bit larger font size. So you see the inputs there at the top. Now this is your model, so you can add whatever other different parameters you think might be needed. For example, if you wanted to use a 3-layer network, you could add an FC_FC3 units parameter here to define the number of hidden layer units in a third fully connected layer of the network. So again, just do whatever makes sense for your application, and as you're working through your navigation project and later projects, you may end up finding you need to do quite a bit of manipulation of these different sets to come up with a set of hyperparameters and a architecture that works for your application. So again, there's only 5 lines of code in this initialization. It's pretty simple, straightforward. You first just call the superclass initialization to perform all the initialization that's defined in the PyTorch nn.module, and then define the seed that you're going to use, which was passed in as one of the parameters. So that if you want to do recreate the same exact implementation starting from the same place, you can recreate a set of results that you've previously seen. Or if you want to try different random seeds to see how things vary based on the seed, you could do that as well. And then next things are the definitions of the different layers. So here we're just defining 3 different layers: FC1, FC2, and FC3. They're all of the nn.linear container class, so they're all fully connected layers. The first one, starts with an input of state size. It outputs a number of units of size FC1 units. The second layer is takes another hidden layer, takes all the FC1 units and as input, and then fully connected layer to the number of FC2 units that you defined. And then the last layer is the final layer of this network, takes that output of FC2 and outputs it to a set of neurons on the output of size, action size, and that will be where all the actions are presented as outputs. Okay, and the last thing in your model is to define what to do, how this network works to do a forward propagation step. So that method is called forward, and forward takes a set of states as input, and then here again this is fairly simple, but you're basically taking the FC1, passing in the state information you got as input to this forward pass. Passing it through FC1, and then performing a ReLU activation function on that result. And then you take that X value in that first line and pass it into FC2. So now we're feeding it through the next layer of the network. And again, on the output of that layer, another ReLU activation function. And then again, the last thing that's done is to take that output of FC2, pass it through the third layer, which produces the state outputs. and return that to the caller. So pretty straightforward. That basically is all that's required to implement a fully working neural network for doing deep reinforcement learning. Now, I mentioned, let me just go back a couple slides. One thing that you may find you need to do is to use some batch normalization. So if you decide that that's needed, take a look at nn.batchnorm1d, and you can see how to implement a one-dimensional batch normalization on the inputs to particular layers. And when you define the init function for your QNetwork class, you'll need to define those batch norms basically the same way as you define your FC1, FC2, and FC3 here. They just become a new layer definition within the network. And then once you've done that, you also have to include that step in the forward pass, just to show how you would, for example, take a batch norm of the state before you pass it to FC1, and then maybe take a batch norm of X before you pass it to FC2, etc. So if you decide that that's needed, take a look at that. There's some examples in the PyTorch documentation, or you can take a look at many other implementations of Q networks that you might find on the web, and it'll often include a batch norm step as a way to optimize the network performance. Okay, the second half of this problem is going to be the agent side of things. So I mentioned at the outset here that the two major files that you typically see as utility functions used in your implementation of a deep reinforcement learning program has both a model.py and an agent.py. And in this case, our agent's a DQN agent, so it's appropriately named DQN agent.py. And again, this is from the Lunar Lander project. Excuse me. So here's the import section. And now agent.py, actually, you'll need to take a look at it when you use this class in your implementation. There's quite a bit of code here. I'm not going to go through it totally line by line. I'm going to concentrate on the sections of it that really have the PyTorch sections that are important to see how PyTorch is used. There's lots of other things that are done in this module that are not PyTorch specific related, but more related to the agents, particulars of the agent itself. So we'll touch on mostly here on the PyTorch part. So on the imports of DQN agent, you can see we're importing the model from our QNetwork. This is the class we just talked about, the class that we just defined. And then you'll see the first two imports there are the ones that we've seen before, same ones basically as we used in the model. And here's a new one at the end, torch.optim. And this is where you would import a optimizer to be used. I think Lunar Lander uses the Atom optimizer, which we'll talk about here in a second. But there's many optimizers to choose from. Atom is just one of them. Traditional stochastic gradient descent, of course, is another one, and several others. Pretty much, anything that's commonly used and something that you're familiar with from any of your working with neural networks. There's probably an optimizer in PyTorch that implements that optimization algorithm. So there's the documentation page if you'd like to take a look at that in more detail. So here's the init method. And just before init, I also included a device call here. This is something you want to do to make your code be kind of agnostic as to whether or not you have a GPU available or whether all the code has to be executed on the CPU. So typically, this is what's done to make that agnostic choice. You can have a simple statement of device is a torch device and use CUDA :0 for channel 0 of the first graphics card basically in your system. If the NVIDIA CUDA libraries are available, then it detects that card as being present. Otherwise, it sets device to be CPU, and then from then on, everything you do just references device, and your code will run equally well on a CPU or on a GPU. So that's a nice thing to have. So when you initialize your agent, you basically have to pass in the size of the state space that you're working on. This comes from the environment, and then you also provide the size of the action. This is the output of the network. It's the size of the number of actions that are possible to be taken. And I recall DQN as It's a discrete action space, so these are basically the number of discrete actions that are possible from your particular environment. And then here below, we see we're instantiating actually two different copies of that Q network model. DQN uses the concept of a local and a target network, where learning takes place initially on a local network, and then slowly it gets propagated to the target network. And that helps stabilize learning in the environment, stabilizes the agent's activities. So here's where you instantiate those two networks. They're basically the same in terms of state size and action size. It's just that here you get two complete networks from that same class that you had defined. And then here we talked about the Atom optimizer. So here's where we define the optimizer to use, and we are using Atom from the Optim package that we imported earlier. Just a real quick, Atom is a little more complicated than stochastic gradient descent. It does similar things. There's lots of different optimizations it makes. The major one really is that instead of having a common learning rate all across the network for all time, it keeps track of gradients on a weight-by-weight basis in the network, and then optimizes the learning rate based on how each one of those weights are changing. So if there's a lot of change in a particular weight, it will automatically lower the learning rate. If there's not much change, it will automatically increase the learning rate. So it really learns much better and more consistently than stochastic gradient descent. And so it's a very commonly used optimizer. So as I mentioned, there's several different methods inside this DQN agent, and one of them is the ACT method. This basically takes a forward pass through the network, and given a state, the network selects the best action to take. And this one, this example just takes the greedy action. You could modify this to add some extra code, and you probably should do that to do epsilon greedy, where you would actually have a random choice of taking a random action. But this particular one just shows an example of taking the greedy action, the best action. So starts with getting the state by getting a state tensor by taking the NumPy state vector and essentially converting it to one-dimensional, turning it into a torch tensor, and then sending it to the device that you selected before, either your CPU for processing or to a execution graph on your GPU, so one is available. The next line is important. The second line of code and the last line kind of go together. Since we're doing a forward pass here, what we first have to do is put the network into evaluation mode so that it won't be calculating gradients. Then we do the forward pass, and then we set it back into train mode at the end so that it can learn after this ACT function is propagated through. So with the torch.noGradients, that's basically we're doing a forward pass, so there's no need to store the gradient information, and you're going to achieve the action values by doing that forward pass by passing in the state vector and then essentially doing a forward pass through the network and producing the action values. And those will get returned from this method. Okay, the second really PyTorch related method is the learn method. So while action is a forward pass function to get a set of actions, the learn method is really concentrating on the learning. So a lot of back propagation and defining what your loss function is, and then doing that back propagation step using the loss function. So the learn method is where you define all those activities. You'll pass in to learn a set of experiences and the gamma discount factor from the Bellman equation. And experiences, you'll find is really a collection of a set of states, actions, rewards, next states, and done flags. So here we, in that first line, we pull out from the experiences all those individual parts. And then we're going to predict a Q value. So we first, on the target network, we pass in the next state, which we got from the experience, and use that to obtain a Q value for that next state. And then we use the Bellman equation to for the target estimate what we think that the Q value should be. And as you recall from the Bellman equation, that's basically the reward that the the environment gave us, plus the discounted value of that QTarget next state that we just obtained. And that is basically the best action we could take in that state. So I might mention that QTarget's next. When we pulled that out, we saw that that was, looks like I lost the share here just a second. Let me reshare the screen. There we go. Okay, so notice the max function there. When we calculate that next value, we want to get the maximum action, the maximum Q value for the best action we could have taken, the greedy action in that state. That's part of the Bellman equation for that QTarget's definition. Then the second thing we're going to do is on the local network, we're going to actually take what the local network thinks the Q value is. And then our loss function is actually what we expect from our local network to have for Q value and what the Bellman equation would give you for the Q value. And we basically use a mean squared error loss between those two as our loss equation. And then that's used by the optimizer to do the backward pass, as you can see in the last 3 steps here. And that basically is how the network learns. So it's really a little maybe confusing the first time you see it, but PyTorch is really pretty straightforward in how you can define things to happen. It's very compact and easy to express what it is you want to have done, and all the work really gets done. Heavy lifting is done by those all those different methods that PyTorch makes available to you. So that really is what I wanted to talk about today. In summary, we talked about how we can use PyTorch to build a model of a neural network, and we use DQN as an example model. We saw that was really pretty straightforward. You just define the layers that you have and then hook them up in the forward pass to make the network understand how to process a forward pass through that network. And then we looked at a common agent in deep reinforcement learning for discrete spaces, and that's the DQN agent. And we looked at how PyTorch is used in that agent. First, by defining an optimizer. Again, in our case, we used Atom as an optimizer. And in the ACT method, we used forward passes to obtain the actions based on a set of state inputs. And then in the learn method, we looked at how we tell PyTorch how to do backprop to do the learning. So that basically is what we want to talk about this evening. If you have any questions about this topic or anything else in the deep reinforcement learning program that we're working with, we're going to have a Ask Me Anything session on Slack immediately after the live webinar. So feel free for the students that are enrolled in this class to take a look there, and be happy to answer any of your questions. With that, I'll talk to you next week. Bye.